In this video, I'll be teaching you guys how to prove arguments with quantified statements by using the rules of inference for quantifiers. Now, if you don't know what those are, I'll have a link down in the description for my video explaining what those are. But if you do, this is a perfect place for you because I'm going to be working through some example proofs. And hopefully by the end of this video, you guys can solve any proof with quantified statements. So first things first, let's go ahead and remove the quantifiers. So you can't really use any rules with quantifiers, right? So you need to remove the quantifiers first. Kx. And in order to remove them, of course, I need to just write down given. Right? So this right here is just the given part. It's one of the hypotheses. And as I said in previous videos, you can write down given or hypothesis. Both of these work. Right? But hypothesis. Both of these work for the reasoning for just writing down one of the hypotheses. Right? So given, actually I should undo so I don't have to write given again. But the next thing we want to do is remove the quantifier. How do we do that? Well, since this quantifier is the there exists quantifier, this little backwards e, we can use existential instantiation to remove it. And the outcome of this is C is particular. It's a particular element of the domain. And JC and KC. All right. So this right here would be existential, what space? Existential instantiation. And I might have to abbreviate this because I'm running out of space. So existential instantiation, and of course we need to write down the number. So this right here is existential instantiation for number 1. What does this number 1 stand for? It's the step that we used for existential instantiation. So what do we use this rule of inference on? Well, we use it on this, right? What step is this on? It's on number 1. So of course we're writing down 1 next to existential instantiation. So on top of the reason why we did something, we also need to write down the line number that we did that little rule of inference on. We can then now simplify this. So we get KC using simplification. Of course, the line number we use this on is number 2. So simplification number 2 is what we use this on. What we use simplification on. And remember, simplification, all you can do with simplification is just write down on a separate line separating something that is split by the AND operator. So this right here is the AND operator here, and this section right here is JC and KC. So all we did with simplification was just, separate this section from this section because it is between the AND operator. All right, now that we have that, we can't really do anything with this, and that's because the final step of our proof, the final part of our proof is L, and L is not in here, okay? So in order to use L, we need to take something out of this quantifier here, right? So let's write down the quantifier, Kx dash L. And you might be wondering, where's the, L of x? Well, L is just a proposition in this case. So you can actually use propositions with predicates, and the rules still work, all right? It's just, this right here just isn't a predicate, okay? There's no variables, there's nothing changing up the statement. So it's just a proposition. Just keep that in mind. But this right here is a given. 5. What can we use to remove the quantifier? Well, we can use universal instantiation. So universal instantiation. And what line number are we using in universal instantiation on? Number 4. Right? Line number 4 has the quantifier. So let's write down C is particular. And I'll tell you why I'm writing down C is particular in a second. So this is K of C dash L. Now, why am I using particular? Why am I not using arbitrary, right? I thought this was the for all quantifier. You should write down C is arbitrary for the variable. Well, here's the thing. For the for all quantifier, you have options. You can write down particular as a particular element or an arbitrary. It doesn't matter, right? You can use both for this for all quantifier. You have options. Now here's the thing for the there exists quantifier. You can't use arbitrary here. You cannot name an arbitrary element of the domain with this there exists quantifier. You must use particular for this right here, for existential instantiation. Okay, you must use particular. But for this, you can you have options, all right? Now, here's the important thing to note. When you're referring to a particular element, when you use the same variable, you're referring to the same you're referring to the same element in the domain. So let's say the domain was 1, 2, and 3, right? And let's say C was equal to 1, right? If I write down C here and C here, we're both referring to 1, right? That element in the domain. So keep in mind, you need to change the variable, right? If you want to choose a different particular element of the domain, you need to change the variable. So C is equal to 1 and C is equal to 2. That doesn't make sense. What if we're referring to 2 down here? Well, you need to use D is equal to 2. So if you're referring to a different element of the domain, you can write down D. But in the case for this, we don't really have to care about that for now because, well, it doesn't even matter, right? C is particular. We have this little operator here. We have this quantifier here. You can choose whatever particular element of the domain you want. Of course, to make it more simple, we'll just choose the same one, okay, as before. So KC-L, this right here is just simplification on number 5. And the next line, we have KC-L. Well, what can we do with KC-L? Well, we have KC-L. And we also have this guy up here too, right? But this says J and K together. Here's the thing. We can actually use simplification, again, because there's an AND operator here. We can use simplification again to separate K. We can separate K from J. So we can get K by itself. So KC. This right here is just simplification on line number 3. Oops, wrong color. Line number 3. So now that we have that, what can we do? Well, here's the thing. We're trying to isolate L. And what's the perfect rule of inference for this? The perfect rule of inference for this is modus ponens, right? Modus ponens concludes this right here. And we're exactly looking for L. So with L, we use modus ponens on lines 6 and 7. Oh, hopefully that meme is still alive in the future. I feel like I've mentioned that so much throughout my videos. 6, 7, 6, 7, 6, 7. That's because it's a big meme right now, okay? But L right here is the final conclusion we're looking for. So this right here is the end of the proof. Once we prove L using, all of these steps over here, that's the end of our proof. Now keep in mind, using the rules of inference, notice how I can go back steps, right? Notice how I can go back a step. Well, that's because by using the rule of inference, you don't actually destroy anything, right? You don't, once you go into the next step, does that mean the previous steps are just automatically gone, right? That's not the case. You can use anything previous, right? You can use anything previous in order to prove whatever you want. All right, nothing is, destroyed. Nothing is unusable by the end of your proof. Okay, like the laws of propositional logic. The laws of propositional logic remove the previous steps. Okay, but this one you can use previous steps like this, like this, like this. Notice how you simplification on number 3, right? And we're on number 7. This works. Okay, but let's move on to the next problem. Let's go ahead and prove this. And my voice is a little, I don't know, it might be a little snobby right now, and that's probably because I have allergies. Yes, I have very bad seasonal allergies, and I very much hate it. And also, my throat's a little sore, not for the reasons you think it is. My throat's a little sore because I was yelling very loudly at a concert yesterday. I'll tell you about that later in this video, of course. But let's finish this problem first. Okay, let's talk about that next. Let's talk about that concert next problem. So we have our end goal as the there exists quantifier, but we have for all quantifiers here. Okay. Well, what can we do with this? Well, remember, for all quantifier has options, and we can use a particular element of the domain for this. Matter of fact, we already have a particular element declared, C. So let's use C, okay? So let's write down for all x, p of x dash q of x, right? And this right here is given, remember that. And on the next step, we can use universal instantiation on line number 1, numero 1, to get C. And I'll omit the particular part because we already have that here, and I also need to conserve space. But we can write down P of C dash Q of C. Now, on an exam, you should write down C as particular. Don't get me wrong. Okay, I'm just doing this video as shortcut so my fingers don't cramp as much. But yes, write down the entire thing if you're taking an exam. All right, because they won't know what you're talking about if you just write down C. But notice how we use universal instantiation on line number 1 to remove the quantifier to just get the predicates. Okay, we can use simplification again to kind of get rid of this variable here. So let's use simplification. Very, very useful. I love simplification. You're going to use it in like nearly all your proofs with this. But you can use simplification to just get rid of the little C guy right here. C is particular. And keep in mind, C right here is the same C right here. Okay, it's the same particular element of the domain. Now, let's go ahead and take a look at this. What can we do with this? Can't really do anything. So let's go ahead and use the next quantifier. Okay. So the next quantifier is P of X. Oh my god, it's not P of X, it's Q of X. Q of X dash R of X. R of X. This right here is given. So we need to write a line number. We do not need to write a line number. Ugh, I mumbled that a little bit. But this right here is universal instantiation again. Instantiation again on line number 4. And we can write down C right here. Same C is particular with Q of C dash R of C. All right. And again, with simplification, we can write down just Q of C and R of C by itself. You know, remove the variable, right? Who needs the variable? You do not need the variable for your rules of inference for predicates. For quantifiers you do, but for predicates, no. But this right here is simplification on line number 5. Now, what's the next thing we can do? Well, notice how we have P dash Q, and we have Q dash R here. And remember, there's a rule that could simplify this. All right? So, see how P is connected to Q and Q is connected to R? Well, an easy way for me to recognize this, or to know what we should do here, is when I, interlink all the arrows, and I'm like, since P is connected to Q and Q is connected to R, that also means P is connected to R, right? So I'm not certain if that's the formal way people prove it, but it's one way for me to spot disjunctive syllogism. Sorry, not disjunctive, hypothetical syllogism. Wrong one. That's one easy way for me to spot it. And once you spot this, well, if your answer is simple, right? If your conclusion is simple, isn't it better for you to have simpler and simpler steps? So that's a perfect way to simplify this entire problem. We have this on line 3 and 6. So we can write down P of C dash R of C, right? Because the Q kind of connects P, and R. So this right here is hypothetical syllogism. And we use this on lines, more space for the lines. We use this on lines 3 and 6 to get P dash R. One last thing. We have P dash R. We also need to write down P and C because that's given, right? This seems useful, and the reason why it seems useful is because of modus ponens, right? So with modus ponens, we're getting there. We're almost there. With modus ponens, we can just get R of C, right? And our answer is R of X, right? With this, there exists quantifier. So with the given, we can use modus ponens. And again, I need space to write the line numbers. But we can use modus ponens on lines 7 and 8, right? 7 and 8. To just get R of C. Last couple things we need. What do we need? Well, we need to turn this into a quantifier, right? We have the R of C, but we need to turn this into R of X. What rule of inference does this? Existential generalization. Existential generalization turns a predicate into a there exists quantifier. It adds a there exists quantifier. But what does it need? It needs an element of the domain. And that element is already given in the problem. Particular. C is particular. This right here is given. Now here's the thing about this. We could also use simplification on lines 2 and 5 to get C as a particular element of the domain, right? This still counts. We can use simplification to get that. But since it's already given in the problem, why not use given? And now that is done. We have a particular element, and we also have a predicate with that particular element within it. Therefore, we can use existential generalization on lines 9 and 10 to get our conclusion, R of X. Great. End the problem. Read through the steps. Make certain you understand everything. And of course, if you have any questions, leave it down in the comment section. I usually say that at the end of the video, but maybe I'll say in the middle this time. So this problem right here looks a little different than the other ones, but that's because, and the reason why I'm showing you this problem is because I want to get across a point where your hypotheses don't have to be always more complicated than your final conclusion. This conclusion right here is clearly more complicated than the hypotheses, right? But I said I'll talk about the concept. I'll talk about it a little bit. I'll put a timestamp for you guys that don't want to listen. Okay, now that the haters are gone, and now that you guys are listening to me, I went to a Leve concert yesterday, and actually, I feel like my life is so scattered around these playlists. Okay, you guys are listening. Oh, 100 subscribers here, and then the next one. Oh, 500 subscribers here. I actually hit 500 yesterday. Let's go. Give myself a pat on the back, and thank you guys too for that. But in my, I think my Calculus 1 series, I mentioned that I bought tickets to the Leve concert, and that was a couple months ago, my Calculus 1 series. And now, if you're watching my Discrete Math series and you hear about this, I went to the concert. And not gonna lie, the legroom was horrible. But I like listening to her music in person. I mean, like, it's nothing I couldn't really find on Spotify myself. But, you know, it's a little bit of a different experience when it's in person. Okay. I didn't really find it much better than the Spotify experience. I don't know. Maybe that's just me. But it was quite nice seeing Leve. I've never seen a celebrity in person. She's like the first celebrity I've seen in person. And she seemed like such a sweet person too. She kept saying like I love you guys into the crowd. Very, very nice experience. This was the Matter of Time tour. So let's go ahead and start this problem. So right here we have quantifiers. Remember, we can't do anything with quantifiers. So let's remove the quantifiers. Okay, this right here is given. And by using, this kind of looks like a delta. Hold up. This is not a number 2. This is not a number 2. By using C is particular. Particular. We have P of C here. By using existential instantiation on line number 1. We can get rid of the quantifier, right? Of course, let's go ahead and simplify P of C. So simplification on line number 2. So get 9 for 4. Of course, we need to get rid of this quantifier too. Let's get rid of this quantifier right now. 5, 6. And this right here is given, since it's the hypothesis, so that's our reason. So given, get rid of the quantifier. Let's use the same. Let's use the same variable C as particular, right? Because actually, in our conclusion, we end up just getting one variable x, right? So of course, we want to use the same variable for the particular element, and this is just Q of C. All right, so this is again, let's actually copy and paste the existential general instantiation, so I don't have to rewrite it. So this right here, copy, paste, bring it down. And we did this on line number 4. And again, simplification on line number 5. Okay, so Q of C. Okay, now what can we do with this? Well, we have P of C and we have Q of C here, right? We also have these combined together. Well, here's the thing. Conjunction actually combines two statements together by using the AND operator. Two hypotheses or little steps that you had by using with the AND operator. And we have the AND operator in between here, which is perfect. We're getting closer, okay? So now that we have that, what can we do? Well, we need the quantifier for our conclusion. So let's go ahead and write down C is particular. Excuse me. Conjunction. Right here. Conjunction on lines 3 and 6. Right? And C is particular is just simplification of lines 2 or 5. Doesn't matter. Let's write down 2. So simplification on line number 2 separates the C's particular part between the AND operator and P of C. That's exactly what we want. And once we have this, we have a arbitrary element. Not arbitrary, a particular element. We also have some predicates. So we can use existential generalization to get the quantifier form of this. Q of X, right? And this right here is existential generalization. That's gonna get way too big. Existential generalization. Okay, I'll just put a period in there to abbreviate it. And this is our lines 7 and 8. And look what we have here. This is exactly the conclusion that we were looking for. Okay, let's do one last problem, because I'm kind of dang tired now. I have to go to the gym. Wow, I've been recording for like an hour now, because I had to retake. I had to do a retake because I forgot to put the flipping steps right here, man. I just gave the reasons. But let's go ahead and go to the last problem so I can go to the gym. Well, maybe you guys can already tell this is going to take a good bit of steps to do. So I might skip a couple steps here and there because they're kind of just repeating over and over again, all right? And also I need to save space because I really don't have a lot of space on this MS Paint screen. But first things first, we need to remove the quantifiers, right? So let's go ahead and remove the quantifier, the first top quantifier. So this one is Q of X, and this right here is given, right? And we also could write down 2. So you can write down the next quantifier. Let's do it all in one go. And R of X and number 3. Right. Not R of X, and all of these are given. And we have 4, 5, 6. Let's write this smaller. Okay, I need to conserve some space for now. So 4, 5, 6, and all of these are universal instantiation, right? Because we're getting rid of the quantifier for the for all quantifier. So let's copy universal instantiation. We have universal instantiation, universal instantiation. All of these are copied. Let's put them back to back to back. Let's say this one is for 1, 2, and 3. And we can kind of just remove all of the, so C is arb. Remove all the quantifiers and introduce a new arbitrary variable. So this is P of C and Q of C. And I'm going to omit the arbitrary because we already have one, just to save space and also to save time while writing. But let's write down P of C. Wait. No, there's no parenthesis here. This right here, that's a mistake. That is a mistake. Not PC and RC. We also have not RC. Yeah. So we have these, this, and this. And since this right here has the AND operator, we can separate this using simplification. The rest don't, but keep in mind, yes, you need... Actually, I'm not certain. It depends on the teacher. Maybe ask your teacher, but my teacher wants me to write down the C is arbitrary, or the variable next to connected to the AND operator and the old predicates inside the quantifier. She wants us to write that down every single time. So I don't know. It might be different per teacher, but that's important to go on a teacher by teacher basis for that, or professor by professor. But now we have this. Okay. We're in a space where we can use some rules now. We can use modus ponens, modus tollens, hypothetical syllogism, disjunction syllogism, conjunction, resolution. What are we using? Well, if I look at these two right here, we can actually use resolution. Well, with resolution, let's go ahead and use resolution on lines 5 and 7 and see what happens. So, resolution on lines 5 and 7, right? Let's see what happens. Well, if we use resolution, we actually end up, and if you don't know what resolution is, just search up the inference. But with that, we actually get R of C or Q of C. Right? Now, what can we do with the or? And what can we do with not RC? We have not RC here. We also have the or operator here. Oh. We just want Q. But we can't use simplification on this because of the or operator. So, in what way can we get Q? Well, we can use the modus tonens or modus ponens. So let's put this in the conditional form. So this right here, using the conditional identity, we actually end up getting not R dash QC using the conditional identity on line number 8. Right? And with this, what can we do next? Well, we have not RC, we have not RC here, and we have dash Q. This is modus ponens. Modus ponens. It's perfect. It's perfect for modus ponens. So if we use modus ponens, we'll actually just end up with Q of C. And I need to put the lines. Don't make that mistake again. Do not make that mistake again. Okay, lines 6 and 9. 6 and 9. Okay, what do we do next? Well, let's get the arbitrary variable by itself. So C is arbitrary. Right? And this right here is just simply simplification on line number 4. Wrong color, line number 4. And the last thing we can do, when you want the quantifier, we have Q by itself, and we also have an arbitrary element of our domain. This is perfect. This is a perfect setup to use universal generalization. Universal generalization. On that's terrible handwriting, but hopefully you understand what I mean by this. Okay, that generalization looks absolutely horrendous. But we have universal generalization on 10 and 11. Now keep in mind, universal generalization requires an arbitrary element. Okay, we can't make this guy right here. We can't use to get the for all quantifier using generalization without an arbitrary element. Okay, that you need an arbitrary element for that. Okay, it must be arbitrary. It cannot be particular. So watch out for that, right? But we have Q of C, and we have C. Using universal generalization, we get the for all x Q of x. And that's exactly what we are looking for in our conclusion. So, as always, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thanks for watching.